Where
You want to start?
I want to start. I want to wait a little bit more.
Okay.
It's better to have my people on board before I take off.
Oh, now.
Okay, yeah, there's a healthy audience here.
Welcome back, everybody in present and online to the GSL seminar. So today we're in the SMC. If you were nearby and wanted to show up, I will be monitoring the chat in case anyone has questions they want to ask. Today, Daniel is going to tell us about the Jordan Curve Theorem. Take it away, Daniel.
All right. So, as I said in my abstract, I'm going to begin with some cute combinatorial theorems. Here we have on the board a colored triangle, or triangulation of a triangle. And for those of you in the know, you may already know that this is probably going to be the setup for Sperner's theorem, or Sperner's lemma. So what does Sperner's lemma say? It says that if I have I will occasionally have to move the camera. Okay, so if I have I'll start with Sperner's lemma in 2 dimensions. And then I'll go higher. So consider a triangle T in R2, triangulated in smaller triangles. Is my handwriting large enough to be visible?
Yeah, it's all good.
Okay. And then I'll call these the main vertices. Okay. The main vertices being the sort of extreme points of the convex hull. Okay. The main vertices colored colors 1, 2, and 3. In the picture here, I have 1 is blue, 2 is green, and 3 is red. Okay. And suppose I have a Sperner labeling. I'll define this in a moment. Have a Sperner labeling. Meaning that for every vertex, the opposite face, okay, has only colors that are not the one that is colored by the vertex. So the face opposite vertex VI colored colors not equal to CI. So that is what I mean by a Sperner labeling. Then there exists a smaller subtriangle with all 3 colors as the vertices. Okay. We will begin to see later that this is actually has a topological depth. Okay, but as of right now, it's just a combinatorial theorem about colorings of triangles in the plane. So how do I prove this? The proof is very beautiful in my mind. Okay. So the first thing to notice, or actually, I should actually rephrase this. There exists an odd number of smaller triangles. Okay, and in particular, it can't be 0. Okay, because 0 is not odd, and so there has to be at least 1. And this turns out to be actually very important when we generalize this to higher dimensions. So how do I prove this? Well, I'm going to define the following. Okay. So on the opposite face to the vertex in question, I'll just choose the biggest value. Okay, so in this case, 3. Okay, in general dimensions, it'll be n plus 1. So consider the face opposite that. So in this case, it would be the edge with only blue and green colorings. Because I have blue starting on one of them and green ending at the other one, actually, you'll have to alternate an odd number of times. Okay, the coloring will have to alternate. So in particular, there will be some edges for which the two colors on either end of the edge are different. In fact, an odd number. Okay, so you can think of that as the d=1 case of the Sperner theorem. So I'm going to label with dotted lines these edges, which have distinct colors at the end, and solid lines, the ones with the same color. And in fact, for all of these smaller subtriangles, if they consist of the colors only 1, 1 and 2, I will call them rooms. Okay, so let me just continue drawing my picture. So these lines are all solid. Okay, these lines are solid, and these are dotted. Are the dotted lines showing up well on camera? I'll take that as a yes. So now I have a bunch of dotted and solid lines. Maybe you already see the picture, but we can think of each of these as little triangular rooms. Okay, and the dotted lines will be doors, and the solid lines will be walls. And you can imagine starting on the outside at one of these edges, which we know exist. Okay, I told you that they exist because the colors differ on the ends, and so there has to be an odd number of edges with different colors. I start at the edge and I just walk. Okay. When I enter one of these rooms, I know that because these two edges are different colors, and the other one is either blue or green, there is exactly one other edge that is a dotted line, and one of them will be a solid line. Okay, so in other words, when I enter the room from a door, I will see two other walls, so two other sort of surfaces. I will see one wall and one door. So I have one choice to go. I'm just going to go through the next door that I see. Again, I'm in a room in which the colors are only green, blue. Okay, I just came through a door, so again, I see two surfaces, one of which is the wall and one of which is a door. I just keep going. Okay. So I tour these little rooms, and at the end, I have to end up somewhere. Okay, there's only finitely many rooms. Okay, so there are either two choices. Either I get stuck in a room, okay, or I leave. Those are the only two possibilities. Okay. So as you can see, this path I left. Okay. But what about this one? I'll start here and I'll take a tour. And I end up here. Okay. So this is a room in which actually both are walls. Okay. I color a segment a door only if they're both blue and green and they differ. So this is the only other possibility. I end up stuck in a room. But what does that mean? That means I found a smaller subtriangle that is colored all three colors. Okay. And so my point is I have an odd number of doors on the outside. I have two possibilities. I take a tour starting at a door. I can either get stuck, or I can exit the hotel. If I exit the hotel, that accounts for two doors on the outside. And if I get stuck, that only counts for one. So it must be that because every tour that starts and ends outside knocks out two doors, and there are an odd number of doors, there must be some door in which I do get stuck. Okay, and that proves that by taking these tours, I actually end up in a room in which there are all three colors. Okay, so that's Sperner's lemma.
How do you know that like a weird case
What?
can happen? Oh, can you hear me?
How do we get an odd number? I suspect I didn't write this down. Finally, the number of rooms is odd as follows. Because every room that is reachable from the outside corresponds to one door on this facet, okay, the space.
With odd minus 2 times a movement.
Okay, so here's the argument. The argument is I can spawn in a trap in one of these rooms, okay? There will be one door. Okay, so I just keep walking in the door and I have to end up somewhere. Okay. If I end up stuck in another room, then that pairs up the number of tricolored rooms. Okay. Or I can leave. But the ones who leave, remember, there are an odd number of them because the ones that oh my God, I'm doing this very well. Okay, so I'm going to call these trapdoors because if I walk through them, I eventually get trapped. Okay, so my claim is that there are an odd number of trapdoors. And the rationale is that there are an odd number of doors, period, and all the non-trap doors come in pairs. So I'm going to say that this claim is proven. And then the number of tricolored rooms is odd because if I spawn in a tricolored room, there exists one door. So I take the door and I walk. I either get stuck in another tricolored room in which there's a pairing, or I leave, in which that corresponds to one trapdoor. Okay. So does this sound convincing? Unfortunately, exists one door. Okay. Tour.
Are you only, you're doing, we're allowing large subtriangles, right? Or no?
I think it's really.
Each room is the smallest possible triangle.
Or I guess the question is, if I'm understanding correctly, are we allowed to pair up a triangle? But I think it's really, we're looking for a small.
Yes.
Like a small possible triangle.
Yeah, the rooms are the smallest possible triangles. If I spawn in a triangular room, this is one door, I tour, either I get stuck or I leave.
They're only two, they're exactly two length one.
No, there's three, right? So there's,
There are only 4 red dots.
1, 2, 3.
Oh,
Yeah.
that was
So
my
the
bad.
statement is that.
Okay, I forgot the upwards one.
Yeah. So in this case, we have this guy with a door, and a
Okay,
door,
I buy this.
wall, and then I start here, and then I make a tour, and I get stuck in another room.
Yes.
Okay. So the rooms that get stuck are paired. The rooms that leave are paired with the trapdoors, but there's an odd number of trapdoors.
I thought we were allowing larger rooms.
No, no.
In which case I was like, we were ignoring the large rooms. Okay, this makes more sense.
So the people in the room are convinced. Can I move on?
Yeah, you must certainly make.
Okay. So apologies to everybody who just got earthquake. Now I will use the Sperner theorem to prove the Brouwer fixed point theorem. The Brouwer fixed point theorem says that for any Rn, but I'll just do R2 since I didn't prove the Sperner theorem in general cases. Although the proof is exactly the same. Okay, you start, if I want to prove in R3, then I have a tetrahedron. And now the base, there are an odd number of doors. Okay, then I just make my tour, and then by the same argument, okay, almost verbatim, if I replace the word 3 with the word 4, okay, then I yeah, for general values of 3, then I prove in the theorem in all dimensions. Okay. So I'll just say R2. If I have the unit ball, a closed unit ball, and a continuous function from the closed unit ball to itself, then it must have a fixed point. In other words, f of x equals x for some x. And if I just wrote an n there, this is again verbatim. So why is this true? First, note that the theorem is sort of invariant, I guess, if I have a homeomorphism of the ball. Okay, so if I prove it for any thing that is homeomorphic to the ball, then I've proven this theorem. Can replace the ball with anything homeo to it. So I'm going to consider the two simplex, or I don't know, is this called the two simplex? Okay, and then I have a two simplex, which is the convex hull of 3 points. Okay, and every guy inside has what's called the barycentric coordinate. This comes from the fact that every point inside of this convex hull is a weighted linear combination of these 3 points. Okay, so every point inside P is equal to the sum lambda of these vertices. Okay, where these guys sum to 1. So each point inside has a unique label by 3 numbers. Okay, and those are called the barycentric coordinates. So now that I have my coordinate system, I can tell you what the coloring that I will apply to the simplex is. Okay, so first, suppose I have this self map of the simplex. Okay, I'm just going to choose a fine grid of this, so a fine triangulation of this. We choose triangulation. You can have some sort of canonical choice like the barycentric triangulation. Okay, you just choose the center of mass, connect all the points, then you. This is important because eventually the diameters of that will go to 0, and we won't be in fact using that fact. Okay, so for now, let's just choose the triangulation. Choose the triangulation. And I have a function f from s to s. Okay. And I'm going to use the notation, it maps W1 through W3 to W1 prime, W3 prime. Okay. Maybe that's terrible handwriting. So there are 3 numbers here that describe a point in the simplex. Okay. Whatever the function maps it to, that's another 3 points, and I'm going to denote that with primes. So for this triangulation, there are finite limiting points. I will now tell you how to color them. So the Sperner labeling. So for W, the vector W of 3 numbers, I'm going to call its coloring the label or the coloring L of W. I'll define that to be some J such that Wj prime, okay, is less than Wj. You can choose some canonical J by choosing it like to be the first such one. I'll mention in a moment that, and in fact, this is well defined for all W, but for now, let me explain what this means. So Wj prime less than Wj. Wj, remember, is the weight associated with the jth vertex. Okay. The higher the weight, the closer I am to the vertex. Okay. If the weight is 1, for instance, I'm just the vertex. Okay. So the fact that W1j prime is less than Wj means that I'm moving away with respect to the barycentric coordinates, not like Euclidean distance or whatever, but in terms of the barycentric coordinates, I'm moving strictly away from the vertex Vj. Okay. So it may be like a little weird. I admit it's a little weird. I don't have too much intuition for how someone would come up with this coloring. But at least now that we see it, it should be clear how to color it. Okay. If the point is moving away, according to the map F, I'm going to color it the color J. So claim it's well defined. What does it mean for it not to be well defined? It means that there is no J, so that this is true. So if no J, such that this is true, then I get that Wj prime is less than Wj for all j in 1 to 3. Okay. But remember, the weights sum to 1. Okay. So if the weights sum to 1 and they're pointwise have an inequality, then in fact they're equal. Because the sum Wj equals the sum Wj prime equals 1, this actually forces Wj equals W prime. Okay, but this is a fixed point. Okay. So I'm saying that assuming, for sake of contradiction, no fixed point, then this labeling is well defined. Okay. Any questions about the labeling? Okay. Furthermore, it is a Sperner labeling because if I'm on this edge, I cannot be possibly moving away from this guy. Okay, there's no more place for me to go. And so, in fact, all of these colors are not this color. Okay. So if I label them 3, 1, and 2 again, vertex 3, vertex 1, vertex 2, then all of these guys will be colored color 1 or color 2, and never ever color 3, because this inequality is not satisfied. Okay. So what does the Sperner theorem tell me? So now I can apply Sperner's lemma. It tells me that I have a tiny triangle with all 3 colors. Okay, now take a bunch of triangulations. I call them Bn for barycentric coordinates. Okay, so I can take a barycentric decomposition of the simplex. Okay. So finer and finer triangulations of the simplex, okay, and such that the diameter goes to 0. Diameter of all the tiny triangles go to 0. Okay. And now what happens? I have a bunch of tiny triangles whose diameters go to 0 that are all tricolored. Okay, so I have a bunch of tiny triangles. Diameters going to 0. Tricolored tiny triangles. Okay. So I'm just going to focus on, let's say, the red vertex, okay, vertex 3. Okay. There are infinitely many in a compact set. Does anybody know what I'm going to do next?
This is sequence of it.
Oh, Bolzano-Weierstrass. Okay, so this is the only limit that I'll take in the entire talk. This is the only appeal to go from finitary methods to infinitary methods. So one application of Bolzano-Weierstrass tells me that actually there is a point that is the limit of infinitely many red vertices in these triangles. I'm going to call them triangle N. Okay. Does this statement, yes?
Do you just get that you get infinite sequence of triangles converging?
I'm focusing on the red vertex.
Right, that's what I meant. Oh,
So I have a P, which is the limit of the red vertices of the triangle. But in fact, because the diameters of the triangles are shrinking, all the other vertices are also going to P. Okay, so the blue ones are also going to P, the green ones are also going to P. Okay, so because the diameter is going to 0, this dude's of blue and green vertices also converge to P. Okay. Okay. They're the same limit. They're the same limit. Okay. They're the same limit. But what does that mean? Okay. When I color them red, it means that that Wj prime is less than Wj. Okay. So in the limit, the inequality will still hold at the cost of an equal sign. Okay. So in the limit for P, where W equals to P, okay, this is what will happen. And this will be for all J. because everything is tricolored, okay? So for all three colors, this inequality will hold because they held for each of the triangles, and then I took the limit, and then that introduced the less than equal. But I argue that whenever this happens previously, this means that Wj prime equals Wj. And so I have found my fixed point. Okay. Thank you. Okay, so this is a beautiful proof of the Brouwer fixed point theorem from Sperner's lemma. Okay. Any questions about this so far? So that's BFPT, okay, the Brouwer fixed point theorem. And now I will prove two more Brouwer theorems. Okay.
There's one question in chat. Someone wants you to revisit the construction of L of W.
Okay. L of W is defined to be the color J. Okay, so I'm going to color the point W, the color J, if Wj prime is strictly less than W of J. Okay. Let me read this question. Does this, and then I said that in English, this means that I'll color the point W, the color J, if I'm moving away from the vertex Vj. Okay, where away means away in terms of the barycentric coordinates. Okay, it's possible to move away in terms of the Euclidean distance without changing the barycentric coordinate. Okay, so I do mean moving away with respect to the barycentric.
The question asks, should that be Wj prime less than or equal to Wj instead of greater than?
No. Because the reason it's strictly less than is because that will, otherwise these could be color 3. Okay, so the reason it's strictly less than is to guarantee the Sperner labeling property that everything opposite of 3 is not colored 3.
Or just in the if not, then.
If
Very well
Wj
defined,
such
if-
as-
Oh, sorry. This should be the other inequality.
That's the same one.
But it's the same argument. Okay. Yeah, so this is the negation of this. I just forgot my inequalities. Any other question? Okay. Okay. So two more Brouwer theorems. There's the Brouwer, I'll call it the hex theorem. I don't know if I'll be able to explain it in this talk. I had it planned, but there's still the Jordan Curve theorem. I'll call it the hex intersection theorem. Okay. And if there's time, I'll tell you why I call it this. But the point is, if I have the square -1 to 1 squared, and I have two paths, okay, I'm going to call this V for vertical and H for horizontal. And I want H to start. Okay, so both of these guys are functions from, let's say, 0, 1 to the square. Okay, and I want, oops, that's not an H. I want H to start here and end here. In other words, I want H1, which is the x-coordinate of H, at time -1 to be -1. And I want H1 of 1 to be, okay. And there's a similar condition for V, which I will not write down. The claim is that then there exists S and T, so sometimes at which they cross. This is why I call it the intersection theorem. So at least this part makes sense. Okay, maybe not the word hex. So the proof is, let's define a new function. I'm going to define a function from the square to the square. And I'm going to define it as HS minus VT over the L infinity norm of the same quantity. So in other words, this is radial projection to the L infinity unit circle, which is the square. Okay. So the L infinity unit circle is the square, the boundary of this guy. Okay. And so what I'm doing is I'm taking advantage of the fact that, okay, sorry, I forgot to say the magic words. Assume, for the sake of contradiction, this does not happen. Okay. Then h of s and v of t will never be equal. And so this thing, I'm not dividing by 0. Okay. And so this is well defined. Okay. And now I'm going to project it all to the edge of the square. Now, the Brouwer fixed point theorem tells me that there must exist S0, T0 in the square such that f of S0, T0 equals S0, T0. By upgrading it to 2 dimensions, f is now a function from the unit square to the unit square, but these are homeomorphic to the disk. Okay, so there is a fixed point. But actually this can't happen because the image of f is the edge of the square. Okay, so the image of f is the edge of the square implies that S0, T0 must be plus or minus 1. Their coordinates must be either 1 or negative 1. Okay. That's what it means to be on the edge of the square. But then, for instance, let's say I have that this guy, S0, 1 is a fixed point. Okay, if S0, 1 is a fixed point, then look at f of S0, 1. This is equal to sorry, this must equal S0, 1, right? But look at the second coordinate. The second coordinate of f, f2 of S0, 1, is equal to h2 of S0 minus v2 of 1 over the same thing in L infinity. But what is v2 of 1? v2 of 1 is 1. Okay. I end at the top of the square. So if I subtract okay. So h2 of S0 is in negative 1, 1. v2 of 1 is equal to 1. And so this quantity is actually less than or equal to 0. So this quantity is less than or equal to 0. But I just promised you that it's 1. Okay, so that can't happen. So this radial projection idea will actually show up again right now. Questions on this intersection theorem? Okay, this is actually the key to the Jordan Curve Theorem proof. Okay, I will be using this theorem like 8 times, okay, in the course of the Jordan Curve Theorem. Okay, I will speed on ahead. This is the second Brouwer theorem. This is the Brouwer. I'm calling it the no ripping theorem. There's probably more sophisticated ways of saying this, but I think this is very evocative, and so I'll just leave it at this. So if I have f from D to D, where D is now actually the disk, okay, not a fake disk like the square, but an actual disk, which preserves the boundary, that is identity on the boundary. Okay. Maybe I'll say this. There does not exist a continuous f from D to D that is identity on the boundary that misses a point in the codomain. Okay. So this is why it's called no ripping. Okay, if I have a map from D to D, I cannot rip a hole and miss a point to P in the codomain. Okay. So this is nice statement. Why is it true? It's true by the same sort of idea of radial projection. Okay. So assume that exists such f, okay, from D to D minus a point P. Okay. Consider radial projection G from D to the boundary. This is radial projection. And this is continuous. Okay. If I'm missing this point, okay, And the result is continuous. I'll just assert this. You can epsilon delta your way through this if you want. And finally, let's consider a rotation. Okay, so a rotation from the boundary of the disk to itself by, let's say, at 180 degrees. Okay, doesn't matter, but I just need it to be non-zero. Well, then now consider the composition. Okay, consider the composition. First do F, then do G, and then do rho. And this is a map from D to the boundary of D, but that's in D. Does this have a fixed point? No, because everything in the interior of D gets smushed away to the boundary. Everything on the boundary stays identity on these two steps, right? F preserves the boundary, G preserves the boundary, but then the rotation twists this off. Okay, so this has no fixed point. Okay, and the two things to look at are interior of D. F smushes to the boundary, and then the boundary of D, rotation, what's the word?
We
Yeah,
have one polite request to slow down, and the question is the origin,
P is any point,
any point.
any point. Okay. You can always homeomorphically push it to the origin. It doesn't matter. Unfortunately, the Jordan Curve Theorem will not allow me to slow down. So, you'll just have to watch me on half speed. Okay, the greatest honor as a mathematician.
Well, because if P is any point, why is radial projection?
That's at the beginning.
Radial from P, right? You start at P, and then you just push outward.
If you want, you can also do like what, a mode. What,
Yeah, Mobius transform,
P to the origin.
conformal mapping,
Conformal
la
map.
la 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 la.
Conformal map P to the origin.
What I mean by radial projection is just have P and then push everything away from you. Okay, just P is the the stinky CS major. Does this work? Okay. Okay, so now I have the bajillion Brouwer theorems, which can all I think they're all equivalent. Okay, you can just prove them all from each other. They're all like they're all like different shades of the same elephant. There's like that story about like the 5 blind men touching an elephant, right? So these are just like the trunk and the nose and the legs of the elephant. I don't know what the elephant is, but there is one. Well, what am I saying? What am I saying? Okay, we are ready to do the next thing. I think I need a board. Okay. Okay. We are now finally ready to tackle the Jordan Curve Theorem. But not really. First, I need a proposition. And maybe I should actually state the Jordan Curve Theorem before we do technicalities. So this is not a technical. This is actually important. So what does the Jordan Curve Theorem say? Theorem. Jordan Curve Theorem. Suppose J is the image of a homeomorphism, or an embedding, I should say, of S1 into R2. So J is the image. Okay. Then R2 minus J has exactly, is open, obviously. Okay, S1 is compact. The image of a continuous function is compact. Okay, the complement is open. Has two open path connected components. Okay, two open path connected components that are disjoint. Otherwise, they wouldn't be called components. Where one is bounded, and the other is unbounded. And furthermore, and both components have boundary equal to J, precisely equal to J. Now, before I do this, does the theorem make sense? So the proposition will actually deal with this boundary statement here. The last thing in the list, which may look like the least important part of the statement, is actually the key to actually proving it. So suppose I have a Jordan curve such that R2 minus J has greater than or equal to 2 components. So I'm going to suppose that I have greater than or equal to 2. I haven't proven that yet. Okay, there might be 1 at this point, but I'm supposing that it has greater than or equal to 2. And now I'm going to prove the statement about the boundary being equal to J. Okay. Then the boundary of each component is equal to J. So that's the proposition. This will prove the second half of the Jordan curve theorem. And it will also help us prove the first half. Okay. So let me do a preliminary claim, lemma 1, let's say. There is exactly one unbounded component. There's exactly one unbounded component. Why is this true? Why is this true? This is because J is bounded. Okay, it's a compact set. It's bounded in the plane. It's contained in some B0Q. Okay, for some radius Q. Okay, the reason I'm using Q instead of R is because I will use R later, and this Q will actually show up in passing. And so remember, this is where Q is. Okay, so for Q large enough, this is true. Okay. So there exists one component containing R2 minus B0Q. This is because J is, let's say, strictly contained in this open thing. Okay. The complement of J is, everything. And so it must contain this. And any other component must also be contained in B0Q. Because if it's not, then it will touch this. Okay. But then I told you that these components were disjoint path connected components, and so they cannot touch. Okay. So in fact, not only are there one unbounded components, all the bounded components live in a big circle. So now let us prove this. So the lemma's over. The proof of the proposition. I will now, okay, so first claim, this is the easy direction. The easy direction is that actually the boundary of the component, okay, so I'm going to start with a component U. Okay, so U is a component. This is contained in J. Why is this true? It's because if not, you will notice that on basically every proof, I approach by contradiction. Okay, and this is famous. Brouwer, in fact, was unhappy with this, and I don't know if I call it the midlife crisis, but like he certainly had something going on, and this was a big part of it. But anyways, proof by contradiction. Okay, no qualms. If not, then exists X in the boundary and X in some other component W. Okay, because if it's not in J, then it has to be in one of the. It has to be something in the complement of J, but the complement of J is just a bunch of components. Okay, so it must be in some component W. But then W is open, and so I have the X epsilon in W. But this is an open set on a boundary point, and so B X epsilon intersects U non-trivially. Okay, but then I get a non-trivial intersection with U and W, which is again not possible because they're disjoint components. Okay. So this claim is not the hard part. The interesting part is, suppose, again, for sake of contradiction, okay, literally every proof that is strictly contained in J. Suppose it's strictly contained in J. then what? Then what? Then there exists a closed arc, A and J, that contains this boundary. Okay. So it's time to use color. So I have the following. Okay, so that's J. And suppose that I have, this is A. Okay, the boundary is somewhere in here. Okay. If this guy, which is closed, okay, is strictly contained in J, if you just homeomorphic back to the circle, then you will see that it must avoid a point, and in fact, it must avoid an open neighborhood. And so take the complement of the open neighborhood, and that will be the arc. Okay, so the arc is actually homeomorphic to the interval 0, 1. So now what? Now what? Okay. We assume that there were greater than or equal to 2 components, and we know that exactly 1 is bounded. Okay, so there must exist some component B, which is bounded. Okay. That's where I'm using the assumption that I have greater than or equal to 2 components. I know 1 is bounded, sorry, 1 is unbounded, and so the other one, which exists because 2 is bigger than 1, it is bounded. It's bounded. If U was bounded on the left side, it can take V to be U. That's totally fine. Now choose any point, choose P and D. Okay. And define D bar, no bar, to be actually B, P, R bar, large enough that contains J. Okay. And in fact, by this argument over here, I can take R to be like bigger than Q or something. All the other components are contained within this guy. Okay, that's why I made sure to prove the lemma first. All the other components are contained within this ball. So now here is the big machinery. Okay, here is something I want to spend a little time on. Recall that A is homeomorphic to 0, 1. I can now extend this. So I have this list of containments. D is contains R, J contains A. A is contained in D. I can now extend this to be a continuous function by the Tietze extension theorem. Okay, so hopefully you remember what that is. It says that if I have a continuous function from a closed subset of, let's say, a metric space to 0, 1, I can extend it to a continuous function on a larger metric space, let's say. So a complete metric space. Do I need complete? Probably. So that it also lands in 0, 1. Okay. So in other words, by mapping between A and 0, 1, I can extend the identity map A to A to now a map from D to A, which I'm going to call R. Okay. R for like retraction. So you can imagine that I have A. Okay. This is contained within this big D. P, okay. And Tietze is allowing me to retract this entire disk to A. Okay. So think about this as sort of the opposite of what the Brouwer no ripping theorem is telling us. The no ripping theorem is telling us that for a circle, there's no way for me to retract a disk to the boundary. Okay. But here, because I'm assuming that this thing is contained in a closed arc, which is an interval, the topology is different, right? Now I can retract. Okay. And so a closed loop, Brouwer says, no, you can't retract. And an interval, I can retract. Okay. So this is the key thing. Okay. This is the key point of this elementary version of the algebraic topology, is that I can retract. Okay. So now, how will this conclude? We can now construct our function f from D to D without P, continuous. Okay. How do I do that? What I do is outside of this guy. So let's say case one. Case one, U is the bounded guy. Okay. Case one, U is bounded. Then I can just take f of x to be R of x for x in U closure, and the identity on x if x is outside. Okay. And the fact that R is the identity on A means that these two things agree in the intersection of U closure and R2 minus U. Okay. Because both are the identity on A. Okay. So what does this mean? It means that in U, I retract all of U to this curve, this black thing. And outside, I'm the identity. You would be like, oh, what about this ripping thing? Like I keep it here and here I retract. Okay. But the picture is misleading because in the picture, it's clear that this thing is bounding it. But the whole point of my assumption is that this is not the boundary of these components. Okay. So I can retract, and then I now end up missing P. Okay. Because P is inside this thing. But all of that was retracted to A. Okay. And a similar thing holds with U unbounded. Okay. Instead, if U is over here, now I just take it to be identity on U, and then in the complement of U, I take it to be a retraction to this thing. Okay. So hopefully I conveyed a sense of why it is true that the fact that if I assume that the boundary is contained in an interval, this retraction is allowed to happen, and then this ripping is allowed to happen, which Brouwer tells us is not possible. Okay. So the contradiction is this tension between this retraction for intervals and the Brouwer telling us that's not possible for circles. Okay. Does anybody want to say anything? Or have I already lost everybody? Okay, thank you, John. Okay, and then, yeah, so these are both continuous. R is continuous by Tietze, and then identity is continuous, and then they both agree, and so by the gluing theorem, blah, blah, sheaf, blah, blah, blah. Okay. Okay, so now we are actually ready to prove the Jordan Curve Theorem. I will now return to the very beginning. Yes.
I mean more. R is from D to A.
Yes.
A does not have P.
Yeah, that's not the whole point. It's
Yes,
missing
but
P.
then why did you say I will construct F from D to D minus
You
P?
need to, so it maps the boundary to itself.
Oh, yeah, sorry, my bad.
Yeah.
I forgot about
Yeah.
that.
Okay. All right. We now flee to the beginning. Can somebody hand me the green and red, please? Thank you. Okay. Goodbye, Sperner picture. I was very proud of you. Okay. So we are now ready to join Curve Theorem. So I have some J, okay, in R2. It's compact, okay. And so there exist 2 points on this J, which are of maximal distance, okay. I can just take the supremum of all distances of 2 points on J, its compactness means that it actually attains that maximum. And so I'm going to say exists A and B and J, such that D of x prime is bounded by D A B for all x and x prime on the curve. So I can now draw this sort of picture. I have J, okay. There's A here and there's B, the sort of extreme points. And now the whole thing is sandwiched between them. I can be more specific, actually, they're contained within this lens shape, okay? If I just draw a circle of the radius between A and B, it sweeps out of the lens and then finds inequality, I actually lie within the lens, okay? So hopefully you begin to see that the picture looks somewhat like the one I drew at the very beginning. You didn't see me draw it because I drew it before you came. Okay, so I begin to construct this picture. And notice, okay, key fact, J intersects, I'm going to call this rectangle R. Okay, so the rectangle R is the thing with A here, I'm going to normalize to be -1, 0. B is going to be 1, 0. And the top of the rectangle is going to be C, okay, for 0, 2. And then D is the bottom of the rectangle, 0, -2. Okay, so there's just coordinates fixing this picture. J intersect the boundary of R is just A and B. This is clear from this sort of thing. The lens, okay, in fact, furthermore, the lens shape intersect the boundary of the rectangle is only A and B, and J is contained in the lens shape. And so this inequality is true. Okay, so now I'm gonna start adding some labels. I already did label it, but we'll see justify it. Okay, so the intersection of J and the line segment CD. Okay, the intersection of J and CD, that must occur because of the intersection theorem. Okay, so this is my first use of the intersection theorem, the first of many. I have a line from C to D, J goes between them. Okay, in fact, there are two pieces of J that go between them, because you just look at the homeomorphic image of the circle. Here is the image of A, here is the image of B. There are two pieces of the circle, and this arc must be one of them, and the other arc will be the other. And they don't intersect again because the map from the circle to the Jordan curve is injective. It's embedding. Okay, so the intersection between J and CD is non-empty. So there exists some maximal thing. Okay. So it exists MC with maximal y coordinate. Okay. And this MC will be in the intersection of J and CD because both are closed. Okay, and closed sets attain their limit points. Okay. So I've labeled it here. MC is the highest point on this line, hitting that is on J and also on CD. Okay. So that's MC. The red. That's MC. And then define JC. JC for C being the top. Okay, so this is the top half of the curve. To be the piece of J containing MC. Okay. I told you there are two pieces. One of them has got to contain MC, the other cannot. Okay, JC is that piece. And then JD will be the other arc. So JD is the other guy. And so that's in the picture I have here. In red, I have JC. In blue, I have JD. Maybe I'll just label it JD, JC. I have JC and JD. And now let NC, maybe I'll say it up here. let NC be the minimum in terms of the y coordinate of JC intersect CD. So I told you MC was the maximum. There will be another thing, the minimum. It is possible that they're the same. So in our case, I've labeled NC here. Maybe it's hard for the people on Zoom to see, but the people here can see that it's labeled NC. Okay, and N for minimum. I couldn't call them both M. Unfortunately, the words maximum and minimum both start with M. Okay, we do a similar process to construct MD and ND. Okay, so plane JD intersect NCD. Okay, so this is the intersection between this guy, and then this thing. Okay, must be non-empty. And that's because I can just extend this line up. Okay, let me actually write it. Because otherwise, again, prove my contradiction. The paths JD and also CMC bar plus NC squiggle plus NCD bar. Okay. So what path is that? That's the path from C to NC, the squiggle, and then the remaining path. Okay. So that's the notation. CMC is the straight line between CMC. The squiggle NC in red is the red squiggly part between those 2 points. And NCD with the line is the straight line between NC and D. Okay. These guys would not intersect. Okay. Why? JD can't possibly intersect that guy because MC is the maximum. So that's not going to hit there. JD can't hit there because that's the other part of the Jordan curve, and the Jordan curve is injective. It can't hit there because I'm assuming that it doesn't intersect. Okay, so if this was true, then they wouldn't intersect, and then I get another application of the intersection theorem. Okay, John is nodding. Ron is nodding. So this thing is not empty, and so I can define now define MD and ND to be the maximum and minimum, respectively, of JD intersect NC. No, yes, NCD. So it's going to be there. I'll draw them. There's going to be oops, I shouldn't write it there. There's going to be MD, and there's going to be ND. Okay. And now observe that MD is strictly less than NC, because MD is on JD and NC is on JC, but they don't intersect. They only intersect at A and B. And so there exists a point X between them. I'm going to label him. So this guy's X. Okay. So this is the first point that is going to potentially be in the interior of my Jordan curve. Okay, I've worked very hard to give you one point in the interior of the Jordan curve. Okay, and then at this point, it's the final stretch. Okay, I'm a bit over time, but to be fair, I started a bit late. So there are 3 more applications of this kind, and then we're done. But I've drawn the picture already, and so there's not much more for me to do. Okay, everybody okay with this picture? So the picture is the most important part. The thing I'm just erasing now is the justification for why I can draw this picture. So now that I have the picture, I don't need this. Okay. Claim the component containing X is bounded. Why is it bounded? Let's call this component U. Component U containing X is bounded. Suppose not. Again. Then U is the unbounded component, the single unbounded component. So there is going to be a path from X to infinity. Okay. So it will definitely leave the rectangle at some point. It will definitely leave the rectangle at some point. And now I will now construct a path that contradicts the intersection theorem. So very similar to this guy, I will consist of 5 pieces, but each of the pieces I will show does not intersect. Okay. And so that's so let me call this point E for edge. Okay, so E is on the edge of the rectangle. It's what happens when I follow this path to infinity and I hit the boundary of the rectangle. So in this case, E is the y-coordinate of E is below 0. Okay, so I'll just do that case.
E is the first that we just put down.
Yes, E is the first time I hit this del R. So consider the paths. There's going to be JD again, but also now C, MC, R, MC, NC, squiggle, NCX, and then this XE squiggle. Okay, this is the squiggly line in black that I've drawn here. And now also the corner, okay, which I'm not even going to try to notate. Okay, it's this corner. So all of these added together, I claim don't intersect. And that will be our contradiction. Why don't they intersect? I already justified why the JD doesn't intersect these 3, right? That's the previous proof I did. It won't intersect these 3 because just using properties of like MD being the maximum. Okay. It will not hit XE by assumption, right? I assume that XE was in the unbounded component U, by which I mean it doesn't hit J, in particular it doesn't hit JD. And it doesn't hit the boundary of the rectangle because the boundary of the rectangle only intersects the Jordan curve at A and B, and neither of these things contain A and B. And so this is true. This claim is checked. And then I have one last claim. There's no other bounded. After this, I'm done. Right, because I just need to show that there are exactly 2 components, one of which is unbounded, one of them is bounded, and I already proved the boundary equal to J. So no other. So suppose, again, a particular contradiction, that existed another bounded component V. Then let's consider the path C MC R plus NC NC squiggle. So the same guys, right? You shouldn't be surprised. Plus that, plus now the blue curve MD ND. Okay, so that's this blue curve between MD and ND. Plus NDD. Okay, so that's this path. C goes to MC, squiggle to NC, straight down to MD, squiggle to MD, then down to D. Okay, and then also. Okay, so consider this path. I'm not going to tell you the other path yet. Okay, this should have been the first thing. So suppose there exists a bounded component V. Okay. And this does not intersect V. Does not intersect. Why doesn't it intersect? Because CMC, that's path connected to the outside component. Okay, so it's path connected to the outside, so it's not going to be path connected to V. MCNC, that's J. Okay, not going to touch it. NCMD, okay, why is this true?
It's in the component of X.
It's in the component of X, right? And I assume B was the other one. Exists other. I should have said other. Okay. And it's not going to hit MD ND because that's again in J. And NDD, that's again path connected to the outside. Okay, so it's not going to hit B. Now what? Because I'm going to call this path gamma. Because gamma is closed. R2 minus gamma is open. Okay. And notice that gamma does not contain A or B. Okay, none of the pieces contain A or B. Okay. So this guy's open, contains A and B, and so there must be little balls around there. BA, BB, that is contained in R2 minus gamma. Okay. Now here is the amazing part. By the proposition that I proved, okay, A and B must be in the closure of V. Okay, so this is crazy. This little technical piece of the Jordan Curve Theorem turns out to be the way we get to the finish line. Right, we're almost at the finish line, right? And for those of you who are nodding, I think you already are there in your mind. Okay, so AB is in the intersection in the closure of V, and in fact, it's on the boundary of V, and so BA, BB intersect V non-trivially. Okay. But then what? V is path connected. So let's say they intersect at VA and VB. Okay, so little VA, little VB, okay, are in the intersection of VA and V and VB and V. Sorry, and V. V is path connected, and so there is a path VA, VB tilde. Okay. But now I add to those the path from VB to V, the straight line path inside the little ball. The ball is disjoint from gamma, so I can just add this without qualm, and I add back in A, VA, straight line. This is the path starting at A, ending at B, that does not intersect gamma. I barely keep my promise. Hopefully that was somewhat influenced. Any questions?
Why do they call it X theorem?
Good question. Why is it called the Hex theorem? Why is it called the Hex theorem? It's because of the game called Hex. So there's a game called Hex, which involves drawing little hexagons. You can imagine that I can keep going like this. Okay, so I'll have a structure like this. Okay, so a parallelogram looking shape. Okay, you just put the hexagons next to each other like this. Each thing is tiled, like has 3 hexagon neighbors on the interior. And the point is that you can play this game. So let's say this is the red side. And then there should also be a blue side. Okay, so this is the finite board, right? I think people play it on like 9x9 or 19x19 or whatever. And then one person is blue, one person is red, and their goal is to connect one of the 2 sides with their colored pieces. And so there's a theorem that every game of hex has a unique winner. Okay, it's not going to draw. Okay, and you can prove it combinatorially. You can also prove it using Sperner's lemma. You can also prove it using the Brouwer theorems. Okay, and this can also prove the Brouwer theorems. Okay. And so this is like one of the pieces of the elephant. This is like the elephant ear or something. They're all part of the same creature. And so there are some nice things. You just Google hex game and then Brouwer. And then there will be like a bunch of papers and a YouTube video that shows up. And it's all very beautiful. I think that if you learn anything from all today, the Jordan Curve theorem is actually not the main star. The main star is this elephant. That's why it's called Hex theorem.
All right, let's thank Daniel again.
you.